Everyone, it's me, Zach, here, and I'm going to teach you the history of the differential equation through impersonations of famous mathematicians. Hello, I'm Gottfried Leibniz. I developed diffq from calculus. Differential equations are essentially mathematical equations that have derivatives of variables along with variables and constants. I found the relationship between dx and dy of any variable x and y. Hey guys, I'm Jacob Bernoulli, and my brother Johan and we worked on differential equations as well, and Gabriel Manfredi published the first book on the subject in 1707. Hey, I'm Leonard Euler, and I developed the use of the integrating factor to derive differential equations. That is all, young lads. Hope you like my historical presentation.
And now for a quick lesson on how to solve differential equations. There are two types. If the equation is separable, it would have to form dy over dx equals some function of x times some function of y. And to solve that, what we have to do is move all the variables with y to one side and all the variables with x to the other side. Once we have that, we can just find the integral of both sides and solve for a solution where y equals something with x plus a constant. Now for an example, y prime plus 10xy equals 0. We do some multiplication division and move the variables around so that we end up with 1 over y dy equals negative 10x dx. And now because both sides are equal, we can take the integral of both sides. So we have this, and the integral of 1 over y is ln of the absolute value of y, and that is equal to negative 5x squared plus a constant. We can raise e to both sides to get the absolute value of y equals e to the negative x squared plus a constant. And the expression with e can be further simplified or factored into e to the 5x squared times a constant. And because e to the c is just another constant, we can express that as a new c. So we have the absolute value of y equals c times e to the negative 5x squared. And because c is a constant that can be either positive or negative, we can just take away the absolute value bars, and our answer is y equals e to the negative 5x squared. What if our equation is not separable? Well, there is also a method to find the solution for all linear first-order equations. And to do this, we need our equation to be in a form y prime plus a function of x times y equals another function. To solve, we would find alpha of x, which is equal to e to the integral of ax dx, and we use that in an equation to find y, the solution. This is an example of a non-separable equation. X times y prime minus 3y equals x squared. To solve this, we need this in the form, So in this case, we divide the entire equation by x. And we have y prime equals 3 over x times y equals x. And now we can find alpha of x, which is equal to e to the integral of negative 3 over x dx, and that simplifies all the way down to x to the negative third. Now we know what alpha of x equals, we can use that expression and all the other expressions from the original equation to use in this. So we have y equals the inverse of alpha of x, which is x cubed, times the integral of alpha of x times b of x. So that simplifies to the integral of x to the negative 2 dx plus a constant. And we multiply everything out, we end up with y equals negative x squared plus a constant times x cubed.
Now a physical demonstration of terminal velocity. Yeah!
Differential equations have a variety of applications in physics, biology, chemistry, economics, and so on. We learned 3 applications of differential equations for Torricelli's law, free fall, and annuity. We can use differential equations and Torricelli's law to solve problems dealing with water draining from a tank. Using the variables that you see in the video, we can set up a relationship between the height of water in the tank and time. We figure out the speed that the water is leaving the tank through Torricelli's law, which states that the speed that the water is leaving the tank is equal to the negative square root of 2 times gravity times the height, which is equal to negative 8 square root of y feet per second. Here's an example. Given a cylinder with a base area of 30 feet squared and a height of 10 feet, as well as a hole of area 1 over 3 feet squared, find how long it'll take for the tank to go from completely full to half full. Starting off with the original equation, we plug in all of the variables. Then we move all of the y's and t's to one side and we integrate to end up with this. Now we have to solve for c. To do that, we'll use the initial condition, which is that the tank is full and the time is 0, and we find out that c is equal to the square root of 10. Now we'll solve for how long it takes for the tank to empty to half. And to do that, we plug in half the original height, which is 5, and then we solve for t, which is 20.8405 seconds. Our next application of differential equations is freefall. Using the variables that you see in the video, we can model the speed of a free-falling object at any time. We can also figure out the terminal velocity of that object, which is negative gm over k. Here's an example. Assume there's an object weighing 60 kilograms. Find the terminal velocity of this object. Alright, we start off with the original equation to find the terminal velocity, then we plug in the numbers, and then we find the answer, which is negative 58.8 meters per second. Our third application for differential equations is annuity. Using the variables that you see in the video, we can model the change in principal of an account over time. Here's an example. Assume the withdrawal rate for an account is $1,000 a year, the interest rate is 5%, and the initial amount is $15,000. How long will it take for this account to run out of money? First, we have to solve for c. Using the initial principal, we can solve for the c value, which is negative 5,000. Now that we have c, we can solve for how long it'll take for the principal to be equal to 0, or when the balance will run out of money, which ends up being 27.7259 years.